So I've got an AC supply here. Over here, this represents the current at the gate. So in other words, this represents how much current. I don't have it up anymore. How much current is going, so the trigger going into the gate, right? That's where we have our potentiometer. So we could say, okay, well, if this represents, the value of current that the gate is getting, and we'll say this is, basically wide open, it's getting a large value of current to the gate, then the firing angle is very, very low, right? Because we know that as that decreases, our firing angle increases, and we got to a point where the firing angle got to 90 and it shut off, right? So let's take a look at over here. So this is the Triac output. So let's take a look at what we would experience here. So I've marked it out from 0 to 180. So starting on the 180 degree, full output of current over here. So I would have something that looked like that. Now, the difference would be, of course, that, well, let's zoom in. The difference would be, of course, that, well, look at this point here. I'll circle it. At this point here, this is our minimum gate current. So really, it's not conducting from this point here where my crosshairs are to the point it conducts, to the point that there is enough current to be able to get it to conduct, right? So we're really not going to see that on the screen. We're going to see something that looks more similar to what you saw last week, right? So none of this would be conducting currently. So all of a sudden, you would see this line like this. And we saw waves like that last week. That was what we were familiar to seeing. So, and this is the delay, and this is that firing angle. And if you're to say, okay, well, if that's halfway between 45, that's about 22.5 degrees firing angle, somewhere around there. So it's going to, I'm just showing as being fairly low. Fairly low, somewhere around 22.5, and it starts to conduct. Well, if we think about this, well, if this SCR is able to, if this SCR is able to fire on both the positive and the negative, the Triac, the SCR only fired on the positive, right? But a Triac can fire on the negative as well because of the way it's these two SCRs in inverse parallel. Well, it must mean that, from 180, so let's do this one here, so there to there, right? So we're looking at this negative pulse. So I'm just going to pull this down, like that. So something like that, right? Now, of course, same deal as if we look at this point over here in the negative portion, we see this right here. Right there. That's the portion. That's the point at which the minimum gate, that voltage increases, and then boom, it's going to start conducting right there, right? So let's take a look at what that would look like in the negative. Well, in the negative, we're not going to see, just like in the positive, we're not going to see any of this conduction happening here. We're not going to see that because we know it's only going to start conducting like right about there. So your output waveform under these conditions is going to look something like that, where it starts to conduct here at that point, and then it's conducting through there. And remember, it continues to conduct past that minimum gate threshold. That's the minimum gate threshold is what you need to trigger to turn it on. Remember, SCRs are hard to turn off unless it's in AC, right? So Triac operates the same way. So that minimum gate current, it starts to conduct at this point, and then it stops because it passes a zero threshold. And then it isn't until you get to the current up here like this, then all of a sudden it starts to conduct, and then that cycle repeats and it continues. So, we're showing that at about 22.5 degrees, somewhere around there. So you can see how that would make sense. Let's take a look at this one here. Okay. So this one here, my current value is less here. So I'm going to see, less amount of conduction, right? So there's my 0 to 180. And, it's certainly going to be, certainly going to be less. So, I'll put it somewhere around there. And then if we look at where it starts to conduct, right here, we can see that it's at this point where that current is now high enough, and it's going to conduct until it gets down to that point, which is a zero threshold. So let's take a look at what that would look like again over here. So, well, again, the reality is that if that threshold isn't being met, then none of this is conducting. This isn't going to be here. So we're going to end up, again, having this line where that firing angle delays the conduction to that point. And then on the negative portion, so this negative portion, as it cycles below this zero threshold, it turns off, but the negative will flow as well here. So now we're into the negative territory, but we're not going to have any conduction until we get past this threshold here. So if we take a look at this one, this threshold here is somewhere around right there, I would say. Okay, so at this point here, it starts to go positive. So just sort of outlining that there, lining that up. So again, there, I'm not going to have any conduction through here. So your waveform should look something like this. And this is exactly what you're going to be doing. And the reason that I go to such lengths to show you this and its relation to the gate waveform is to make sure that when you see a waveform that looks like this, that you know whether or not you're seeing something that's correct, right? And this waveform will continue to conduct, right? So it'll continue to move over like this. And if I had a capacitor, I could activate this portion of it as well. And then as it starts going into negative territory, it starts to conduct. And so I can control the amount of power there, because normally, with DC motors, we take the DC supply and we decrease the amplitude of the DC, and we can therefore control the speed of the motor. But with the AC here, what we're doing is we're actually decreasing the amount of time that waveform is allowed to conduct, and we end up getting less power, but without having to reduce the amplitude. But when you calculate your values for RMS, you're going to see that it is, if I'm at 90-degree firing angle, I'm going to have 50% of my power, right? So another way of doing it. Okay,